Koottandavida from Yale University talking about erasure detection in 3D superconducting dual rail qubits. Take it away.
Thank you. Hi, everyone. My name is Akshay. I'm a grad student working with Michel Devoret at Yale University. We just heard a very nice talk from Shruti about erasure qubits and how they can be used in concatenation codes to improve the threshold and distances. And she also talked about a particular implementation as an example using neutral atoms. Well, in this talk, I would like to show you another type of erasure qubit, one based on the dual rail, implemented in a 3D superconducting cavity. Before I begin, I want to thank my colleagues over at the Yale Quantum Institute and also the organizers for organizing such a nice conference. Cool. So I split my talk into 3 parts. In the first part, I'll briefly go over the concept of erasure qubits, and then I'll describe our hardware, the double-pose superconducting cavity system where we encode our dual rail qubit, and I'll also show you the results of the erasure detection. And finally, in the third part, I'll discuss our the new method that we came up with to perform direct tomography on the 2 oscillator dual rail states, and that lets us extract the relevant rates that we need to characterize our system to tell us whether it's any good at all. Okay. So as you've heard in the previous talk, erasure qubits are very interesting in the context of concatenation codes. Essentially, if you can replace your physical qubits in, say, the base layer of a surface code, which has Pauli errors, with erasure qubits, which has erasure errors, and you can detect them efficiently, then you can increase the threshold and the distance of the code. So one nice way that I'd like to think about this is by taking the analogy with the classical repetition code. So let's say I have a 7-bit repetition code like this, where I've copied my information 7 times. And if you have bit flip errors in the bits here, which is sort of analogous to the Pauli errors in the qubit case, then I can tolerate up to 3 errors in this case. Any more, then I have a logical error. So the distance of this code is 3. But now, say that I have bits which has erasure errors, where the error channel takes the bit to an error state, and I can detect that error efficiently. Well, then in that case, I can tolerate up to 6 errors. I can still decode the information that that was initially encoded. And so now the distance is 6, and I've doubled it. So this is the sort of naive analogy that gives you an intuition why erasure errors help. So going back to the case of erasure errors, Shruti outlined some of the important properties that a good erasure qubit needs to have so that we can think about concatenating them. So I'm going to focus on a couple of them here. So first of all, obviously, we need a system that, under the action of some error, leaves us in an error state or an error space, and then we need to be able to efficiently detect this error so that we can convert this error channel into the erasure channel. And finally, we need a good hierarchy of rates. So basically, the qubit should experience predominantly erasures, with the remaining Pauli errors occurring at a much lower rate. I think the erasure fraction is one way to quantify this. So what I hope to convince you by the end of this talk is that in our system, we implemented such a qubit, performed erasure detection, and that we're indeed in this good regime of hierarchy of error rates. So there are, of course, different types of erasure qubits recently proposed and demonstrated. In the previous talk, you heard about the neutral atom implementation, where you use the metastable states to encode the erasure qubit. And some other types include erasure qubits based on the dual rail encoding. Here is a dual rail qubit implemented using Transmon from the AWS work. I think we'll hear more about this on Friday. And another type is the dual rail encoded in harmonic oscillators in 3D superconducting cavities. So the work that I'm going to discuss here is going to be more of this flavor, the final one, but a different hardware, slightly more efficient and using less components. Okay, So let's see how we can encode a dual rail in harmonic oscillators in the first place and why we want to do that. So the dual rail code is defined using two harmonic oscillators. Here are two of them, Alice and Bob, and they have unbounded Hilbert space with energy levels 0, 1, 2, etc. So the dual rail code is defined with the 0, 1, and 1, 0 energy levels of this combined system. And so these become the code words of your block sphere. One reason why we love the harmonic oscillators is that they have a very simple error model. Basically, the dominant error channel is photon loss, which discretely takes you down the ladder until you're in the ground state. And here we have Alice and Bob, two harmonic oscillators, so they both have photon losses. And what this error channel does to the dual rail encoding is that it destroys the block sphere and leaves us in the error space, which is the ground state of the system. So photon loss, so the bottom line is photon loss takes us to the error space, but this error space is orthogonal to the block sphere, the code space, and so we can detect them. And that's going to be the basis of our erasure detection. And so if we can detect them, we can convert this photon loss error channel into an erasure channel. Finally, I want to know that these oscillators have negligible dephasing errors, especially the ones implemented in 3D cavities. This will be important later. Great, so how can we detect these photon losses? So to do that, I have to use an ancilla, which is going to be a transmon qubit in my case. So let me introduce our experimental system. So here we have our double post cavity system. It's made of aluminum. Essentially, you take a block of aluminum and you drill into it a cavity until you're left with two posts of equal size at the bottom here. So so each of those posts hosts a quarter wave electromagnetic mode, and because there are two of them, you have two eigenmodes in the system. And here I'm just sketching the electromagnetic field distribution of those two modes. And these two modes are going to be my harmonic oscillators, which I'll use to encode the dual rail qubit. These two modes live in this volume right here. And as I mentioned before, I couple both of the modes to a transmon qubit based on Josephson junction. And that lives on this chip right here, which is poking into this cavity. And if I have this configuration like so, these three modes, Alice, Bob, and the transmon, will interact with each other via a dispersive interaction that looks something like this, with some rates chi AQ, chi BQ, and the n represents the number of excitation in each of the mode. And crucially, we'll be using this interaction Hamiltonian to not only do logical state prep, but also erasure detection and tomography. So it's very handy. And here are some numbers for you to glance at. Okay, so let's see how we can use the dispersive interaction to perform erasure detection. So here, what I'm doing is I'm preparing three states in Alice and Bob, 0, 0, 0, 1, and 1, 0. And I'm doing a spectroscopy of the transmon. Basically, what this dispersive interaction does is that it shifts the frequency of the transmon depending on the number of excitations in the oscillators. And this shift is proportional to these chi's here. So if the cavities are empty, or in the 0, 0 state, then the transmon frequency is unchanged. But, well, that's exactly our error state that we have to detect for the dual rail qubit. So to detect photon losses, all we have to do is prepare our system in the dual rail subspace and see if the transmon frequency shifted at all or not. And this is the circuit that we use to do that. And what this circuit does, it queries whether the transmon frequency changed or not. If it changed, then we deduce that we were in the dual rail subspace. If not, then we say an erasure or a photon loss occurred, and we're in the error space. Okay, so this is the result of running the circuit in our experiment after preparing the plus X logical state in the dual rail subspace. And we prepare these states using optimal control pulses. So what's going on here? So each row here represent running the circuit for n detection rounds. So we prepare and perform erasure detection for n equals 75 rounds. So let's focus on the first row here. So what happens is we see a bunch of green, which means the transmon is in the ground state, which means that the frequency of the transmon has shifted, and we deduce that we're in the dual rail code space. But at measurement round 32, right about here, the transmon state changes from G to E, and there, what we deduce is that a photon loss occurred, and the transmon frequency shifted back to its original, to its bare frequency, and we flag that as an erasure. So essentially, what we're looking for is a state change from of the transmon from G to E. But of course, not all state changes means there is an erasure, because the transmon has errors, namely bit flips and phase flip, and also we have infidelities in the readout, and all those can show up as these small islands over here, and that can give an incorrect result. So if you remember from Shruti's talk, she mentioned that we need to have low false negative rates, and that means that the circuit can tell us sometimes that an erasure did not occur when in reality it actually did, so we missed it. And in our system, we characterize this to be around 0.28% per measurement. Great. So now that we have a way to perform erasure detection, we need to characterize it. Essentially, we want to check what it's doing to the logical code space and whether it's actually detecting photon loss or not. And to do that, we choose to perform direct tomography on the dual rail subspace, on the combined Alice-Bob system. So there are different ways to do this, but we decided to measure the density matrix of the system, of the states in the coherent state basis, and for the quantum optics experts in the crowd, we measure the Wigner function. And to do that, we again go back to using the transmon to do it. But because we have two oscillators, Alice and Bob, and the dual rail states are entangled states in the two oscillators, we have to be careful while doing the tomography. That's because to do the tomography, we use this dispersive interaction with these rates, chi-AQ and chi-BQ. And these rates are different in our system, in our case. And that you can see from these spectroscopic peaks. The distance between the two peaks tell you what is the rate chi-AQ and chi-BQ. So in this configuration, when we try to do tomography, what happens is we gain information, or we gain the witch cavity information, essentially, which will spoil the tomography results. And we need to erase this, and to do that, we turn to the transmon again. So what happens is this transmon doesn't only have just two states, it has higher states as well. It's an anharmonic oscillator. And we can selectively drive the higher levels of the transmon. And it turns out we can select, by addressing selectively some levels of the transmon, by using a parametric pump, we can tune and subsequently match the cross-curve rates, chi-AQ and chi-BQ. And now what you can see is the same experiment performed, but in the presence of this microwave drive to do this parametric tuning. And now the peaks are aligned on top of each other, which erases the witch cavity information. And now we can perform the tomography, the joint tomography on the two systems. This parametric pumping is actually pretty powerful. It essentially lets us play with the coupling strength between the modes of the system. In this experiment, we only use it for tomography, as I'll show in the next slide, but in general, it's very versatile and can actually let us do something more interesting and complicated. So okay, formally, this is the functional form of the Wigner function that we're going to measure. Essentially, we have to measure the expectation value of the displaced parity operator. And we do that using this circuit here. So we first prepare the state here, apply displacement pulses to Alice and Bob, and a rotation to the transmon. And then we apply the pump that activates this parametric process. And when we time the interaction to a certain value, given here, we can measure the transmon in the x basis. We end up measuring the displaced parity, or the Wigner function in this case. It's a very simple pulse sequence, which is one reason that we like to do it. And another reason we like it is that we get very nice pictures. So here I'm preparing the relevant states for the dual rail. So we have the error state 0, 0, and the 6 cardinal points on the dual rail block sphere. So we see that the ground state just looks like a blob at the center of the phase space. And whenever you see blue or negativity in the Wigner function, that means you've prepared a quantum state. So these states look like something like that. Also note that the joint Wigner function is a 4-dimensional plot technically, because alpha and beta are complex numbers. So it's very hard to visualize, so I'm only plotting 2-dimensional cuts. Great. Okay, so now that we have put a face to our states, we can do an experiment to visualize what our erasure detection circuit is actually doing. So here I put the 2 circuits that I introduced before together, so erasure detection and the joint Wigner. So what I do is I prepare a plus X state in our system, and then perform erasure detection for n rounds, stop, and then do the tomography. You can think of the tomography as being taking a photo of the state at the end. Okay, so this data shows what happens to the plus X logical state of the dual rail after 0, 10, 20, 30, and 40 rounds of erasure detection. So we can clearly see the plus X state decaying smoothly towards the ground state, which is the 0, 0 state. By around 20 rounds of measurement, we've already lost the encoded state. But because we performed the erasure detection prior to tomography, we can throw away the tomography data whenever the erasure detection circuit told us there was an erasure. And so if we do that, a kind of post-selection, we see that we can reconstruct the data for much longer than before. So the lower panel data is post-selected from the top. And so we clearly see that we are throwing away most, if not all, of the erasure events that occurred. Okay, so that was a very good visual check, but we want to put some numbers on the table. And that's kind of hard to do with the Wigner function, because it requires exponential number of samples to accurately characterize the state. But we figured out a sample-efficient way to do it. Basically, what happens is if you promise me that you will only be in this subspace that you're working with, then you can project this joint Wigner function onto that subspace, which lets you measure the expectation values of the Pauli operators using only a few measurements of alpha and beta. To be specific, with only 16 points in this phase space, we can extract the expectation values of the logical Pauli operators for the dual rail. So when we do that, this is what we get. So here I'm showing the IXYZ expectation values after preparing these 7 states. Using this, this is also done using the same circuit as before, but the number of points are much fewer now. So the 0, 0 state is not in the dual rail block sphere. That's why the expectation values are all 0. The plus X state has positive expectation value for X logical and I logical, and similarly for the other ones. Now, these green bars are not plus or minus 1, and that's because we have state preparation and measurement errors, but that we can account for. Okay, so we go back to the same circuit, but this time we perform erasure detection, and measure the expectation values of the Paulis. And let's see what happens. So here are the results. Let's focus on the top left one for now. So I measured the expectation value of the identity operator as a function of erasure detection rounds. And the circle points are the raw data, and you can see that they're smoothly decaying to 0, indicating leakage or photon loss events. But if we post-selected out all the erasure events, we get these triangle data, which is essentially flat, which means that we're in the dual rail block sphere now. So we also measure the expectation values of the X, Y, and Z operators, and here also you can see the effect of the decaying without post-selection and essentially flat with post-selection. So here the darker circles are expectation values of X after preparing the plus X logical, and the lighter ones are with the minus X logical states. So what we can do now is fit the post-selected data to extract residual Pauli error rates. And if we do that, we we can characterize our dual rail erasure qubit. So what we see is that we extract a erasure probability or rate of about close to 4 decays per millisecond, or about 4.8% per measurement round. And we also measure a erasure error rate of the X and Y logical operators of about 0.17 or 0.2% per measurement, which is an order of magnitude lower than the erasure probability, and very negligible bit flip error rates. So going back to my initial slides, we clearly see a good hierarchy of rates where erasures dominate and the residual Pauli error rates are much lower. And finally, there is a cost for performing erasure detection for longer and longer. The longer we detect, the more chances of an erasure happening, so you'll be throwing away more and more data, and that's quantified by the survival probability, which captures the number of shots that remain after n detection rounds, and that falls off exponentially, as you see here. Okay, so basically I've shown you that we've implemented an erasure detection for the dual rail in our system, came up with a technique to perform tomography and demonstrate a good hierarchy of rates for our system. We can do more work on this system to optimize, to make our detection faster. And we can also think about incorporating this mid-circuit with beam splitter gates, which have been shown recently in these works, which is also something that we're thinking about. Thank you.
Thanks very much, Akshay. I'll open it up for questions.
Hi, thanks for the great talk. I'm really surprised with the Z error rate being very low. Could you comment on why would it be true? Because like one dephasing could lead to...
Oh, sorry. When I mean Z, it's the error rate extracted from the Z logical. So it's actually bit flip here. So, and there won't be any bit flip because there's no process that takes 0, 1 to 1, 0 in our system.
Yeah, sure.
Yeah, and that's why it's very low.
I
Sorry,
see.
the nomenclature is a little different.
And I think you mentioned in the earlier part that you don't have to worry about phase flips.
Yes, there is no dephasing, and that's whereas there's very negligible dephasing for the bare oscillator. But when you couple it to a transmon, you can get induced dephasing, and that's what we're seeing with the PXP, this 0.17 or 0.2% per measurement.
Perfect. Thank you so much.
Use my position to ask one then. How do you think about the complexity of this? You're using now sort of two cavities and a couple of things as a single effective qubit. So how do you think about the complexity of it compared to some alternative approach that was just a single cavity from a scalability perspective?
Yeah, I think when you're thinking about scalability, there are one thing that we can think about is we trade for scalability, higher coherence time, for example. The cavities are known to have higher coherence time than, say, transmons, the dual rail, or any qubits with transmons. So that's one thing that we trade. But another thing is gates are usually slower when you have bosonic qubits compared to just regular transmons. But I guess it's all about, you have to find a balance between what is the final error probabilities that you can measure.
And then I'll ask one other question, actually. What are the prospects for making the erasure measurements much faster?
Right, so right now the erasure measurements are dominated by the fact that we have to separate in frequency the error space versus the code space, and that is set by the value of the cross-curve, the chi here. So one way we can make much faster erasure detection circuit is to increase the value of chi. Next is the readout. We have a particularly slow readout for some reason in our system, and that state-of-the-art readout are like at least a factor of 4 or 5 faster. And so if we incorporate those in our system, that will drastically improve the erasure detection speed.
10x.
I think we can easily go from, right now it's about 12 microsecond to 3 or 4 microsecond easily. And then another thing we can think about is increasing the bare lifetimes of the cavity. So the T1 over gate time is also much higher.
Right, thank Akshay again. Oh, we're ahead of schedule. We've got time, please.
Hey, kind of naive question. I don't know very much about this kind of technology, but it seemed like you had to do quite a bit of work to get the two chi's to be equal so that you no longer could see where the photon was being removed from. But naively, it would seem that you could just put the cavities on either side so that they're equally coupled. Is that not?
Yeah, so you can design a system where you can natively have cross skirts that are equal, and that will completely work. We started off with unequal cross skirts because we wanted to have this ability to dynamically tune the cross skirt as well. Yeah, that's just another thing in our toolbox. But if all you care about was this tomography, then yeah, absolutely, you can design it such that the static dispersive coupling is equal.
Okay, so it's not like you have very sensitive tuning in these devices that you require.
Yeah, exactly.